Okay, so let's talk about what is an integral. And specifically, I would like to talk about what is the definition of an integral. So fundamentally, most fundamentally, what is an integral? Okay, all right, well, here's some options, and let's consider this a multiple choice. I have these options listed in an order, which is very often an order that students see discussions of integrals. And very often, single variable calculus courses, they start off describing the question of, let's look at the area under the graph of a function. And that question is posed, and a first attempt to answer that question is to write down this expression here. This is a Riemann sum, limit of a Riemann sum. And this is clunky and hard to work with, and then a connection is soon made that there's a different way to compute these areas, and that this can be done with certain functions that have this property, that the derivative is the original function. And the connection is that area can be computed with this simple formula. Okay, so that conversation happens, and so now let's return to our question of these options, of these four things. Which one is the definition of an integral? Okay, well, a lot of students think that it's defined as area under the graph of a function. This is not correct. Another large fraction of students think that it is this formula, capital F of B minus capital F of A. After all, this is the formula that's used most of the time to compute the value of an integral. This too, not correct. To most students' surprise, this is how we define integrals in a single variable calculus class. And here it is, the definition of an integral. And you see here this Riemann sum expression here. Okay. So this is our definition, and a bunch of details that have to get said, of course. What is delta x, what is xi star, etc. Fundamentally, then, what an integral is an algebraic expression. It's this algebraic expression. It is a summation. The terms in the summation are products. Each one of these terms has two factors. One factor is delta x. This is often thought of as the width of a subinterval of the interval from A to B. And the other factor is the value of some function. What function is that? Well, that depends on the application that you're thinking about. This Riemann sum expression, then, we take a limit as n goes to infinity, and again, there's our definition of an integral. And one of the problems with this definition is it's kind of hard to relate to. You look at how this is written down. This is a funny-looking algebraic expression. Where's the relatability? Where's the satisfaction? What does this do for us? Common question. So, how do we use integrals? And here's a little schematic of how we use integrals. Of course, most students who take single variable calculus classes are not math majors or are primarily interested in applications, and applications are interesting. So here's how you can use integrals in applications. There's a tremendous number of applications that can be addressed with integrals. And strategically, the way that works is you pick an application, and of which there are many, lots and lots of applications. I've just listed a few here. But pick one. Let's say we're looking for the mass of a one-dimensional rod along the x-axis, for example. Step one, write it as a Riemann sum. That's the first step in the process. That Riemann sum being an integral by definition. And then step two is to compute the value of the integral with the fundamental theorem of calculus. And here's our old friend again, this nice convenient little formula. That convenient little formula allows us to compute integrals, which is great. Okay. All right, now let's see an example of this process in action. Specifically, how do we relate mass to a Riemann sum. Here we go. Here's our rod sitting over the interval from A to B on the x-axis. And let's suppose that our density on that rod is not constant, but it's varied. It depends on where you are. It depends on the value of x. So the density might be greater as you move to the right, as I'll try to indicate there with the uneven shading. Okay, so how are we going to compute the total mass? I can't just multiply density times size because the density varies. Okay, so the big idea is we're going to take this interval from A to B. We're going to chop up that interval into little pieces in the usual way. And we make the modest assertion that the total mass in this rod is the sum of the masses of the little pieces that you get when you chop up the rod. And again, this is a very modest assertion. The total mass is the sum of the little pieces of mass. Okay. All right, now next question, looking at this little piece of mass, well, how much mass is there in there? Well, now here we have a very small piece. You can see that we're going to be talking about, in a limit, and let's not get distracted by formalities here, but the idea is that in the limit it becomes increasingly accurate to say that mass is density times size, because on these little pieces this density is increasingly close to actually being constant. It's never actually constant on the little pieces, but it's increasingly close. Okay, so that's the argument, and then look what we have. We have, sure enough, a Riemann sum. That is exactly a Riemann sum. Let's go back to our definition here. Here is our definition of an integral. There it is, and you see we have a limit of a summation of a bunch of terms, each of which has two factors, one of which is delta x, the other of which is some function appropriate to the application. And in this case, for this application, density is what that function is. This is the appropriate integrand because of how the Riemann sum arguments as relates to our original question of wanting to compute mass. Okay. All right. So this being a Riemann sum, we can write it as an integral, and there you go. This is an integral that you can then compute with the fundamental theorem of calculus up here. Okay. All right. So what we see here is that Riemann sums are the connection between the applications that we're interested in, lots and lots of applications, and the fundamental theorem of calculus, which is going to be the thing that actually allows us to get the final numerical answer. And this is the part that a lot of people focus on. Using the fundamental theorem of calculus, finding those antiderivatives, plugging in f of b minus f of a. And yeah, that's an important part of the process. But very, very importantly, Riemann sums are the first step. Riemann sums are the connection that allows you to take an application problem and write it as an integral that the fundamental theorem can actually address. Okay. All right, now let's consider a related question that often comes up. Very often students object and say, well, yeah, but that formula, that Riemann sum formula, we never actually compute with it. What's the point? How come I can't just use area as my definition? We'll look back to our multiple choice up here. Right? A lot of students think that area is the definition of an integral. So what's wrong with that? And here I have a picture of what that might look like. Let's scratch off area from our list of applications and reinterpret area as being the definition, let's say, hypothetically, definition of an integral. Note the question marks here. indicating emphatically that this is a question we're asking. This is not a statement we're making. So what happens if I do that? Well, I suppose you could make this definition. There's some formal issues that come up of, what exactly do you mean by area anyway? Little complications that we have to deal with. But let's not worry about those. If you make this definition, you could still have a fundamental theorem of calculus. You can still get numerical answers for the values of integrals. Here's what you can't do, though. It's not clear how you connect this definition, area, to all of these other application questions. So, for example, how would you connect the question of mass to area? Same mass question that we looked at on the previous page. How would you do that? What does that look like? Right? I want to know the mass of a rod. What is the nature of this connection to our definition, our hypothetical definition of an integral, namely area under some curve? Well, if you say mass relates to area, what area? There's no area in this question. We have a rod. It's a one-dimensional rod. There's no area in the question. So that's a pretty big explanation that's now due. If you want to say it relates to area of what? And then more importantly, why is that okay? Right? Why is it that you can, what is the reason, what is the rationale behind suggesting that a mass is equal to an area? Now, you can make an argument. Here's an example of the kind of argument that's made. The idea is that, look, we look on little subintervals. On each little subinterval, mass is density times length, little pieces. And then let's just choose to interpret density as a height. And if density is a height, then notice density times length becomes height times length, which is an area, right? And so then the idea then is that adding up pieces of mass is just like adding up pieces of area, and there's our connection. And this is something that is presented to a lot of students, and the problem is it's pretty much just a sloppy discussion of a Riemann sum. Notice we are, just like with Riemann sums, we're cutting into subintervals. We're then adding up pieces of area. We're adding up, specifically then, some function times length. That function being, whatever it needs to be, appropriate to the application. And structurally, that's this. Okay, so this idea of we're going to avoid Riemann sums by just making our definition of integrals area. The problem is that in order to actually be able to make the connections that we need here, that connection goes by way of Riemann sums. Right? So changing your definition of an integral, trying to avoid Riemann sums, does not avoid Riemann sums. If what you're interested in is these applications, which again, a very large number of students are. Okay, and at this point, now let's just think through the sort of the strategy of all of this. If what I need is to compute mass, if I need to connect it to a Riemann sum, then what role is area playing in this story? I don't need the actual area. Here I am back now to, let's just define integrals with Riemann sums. Area is not actually serving a role. Okay, so this is a very important point. This idea that defining an integral as area is sort of an easier alternative to understanding Riemann sums is not. What this is a way of being sloppy with Riemann sums. It doesn't actually avoid them. Okay, so importantly, here's how integrals connect to applications. The applications connect to Riemann sums, and we compute those Riemann sums, aka integrals, with the fundamental theorem of calculus. You've got to have the Riemann sums. Okay. All right. So while we're talking about integrals here, a couple of related things I'd like to talk about. A lot of common questions that come up, students want to ask, trying to streamline their understanding of definition of an integral. And a common question is, well, why do we really need to bother with limits? Let's just think about taking infinitesimal slices of whatever the question is that we're interested in. And of course, students are usually thinking about areas under curves. So let's consider a graph over here, some function, and if I want to compute this area, let's just think about infinitely thin slices. And of course my pen's not fine enough to be able to actually draw something infinitely thin. Okay. So what's wrong with this as a definition? Well, again, we have to go back to applications. We're going to be interested in what I'm going to call real questions. And we're going to want, as relates to those real questions, real answers. And what I mean here by real is real numbers, right? So specifically, we're going to be using real numbers to model the questions that we're interested in. So, for example, you look back at the mass of a rod question, back over to here. We model the question with real numbers in the sense that we describe where we are on the rod by a coordinate on the real number line. Right, everything that's going on in this calculation here is real numbers. We are multiplying real numbers. We are adding real numbers. So our algebraic objects and our algebraic tools are all those of real numbers. Okay, so what? Why can't we use infinitesimals? What's wrong with this idea of infinitesimals? And here's the answer. Infinitesimals, in the context of real numbers, there's no such thing as infinitesimals. Or said differently, any way that you might make sense out of the idea of infinitesimals, they are not real numbers. So, now you can argue that, sure, but, do I really care whether they're real numbers? Well, again, you need to be able to use the algebra. We need the algebraic tools to be able to write down how the calculations go. And algebra requires rules. So I'm going to ask the modest question: if you are going to insist on including infinitesimals in an algebra that involves real numbers, we need to know what are the rules of that algebra. So here's some usually pretty tolerable examples. Most students are pretty comfortable with the idea that if you take an infinitesimal, if you multiply it by a finite number, the result is still infinitesimal. Most students are pretty happy with that. Related idea, the ratio of two infinitesimals. Well, most students are pretty comfortable with the idea that this should be finite. And, a common example that students like to think of, for example, dy maybe as being an infinitesimal. It's a common crutch. Students like to think of it that way. And then maybe dx as being an infinitesimal. And then, dy over dx, students know that's a slope, that's an actual finite number. Okay. And likewise, now let's think of what happens if you take an infinitesimal and multiply by another infinitesimal. Well, surely that isn't finite. So surely that must be an infinitesimal. Okay, so this is what very often students think of as being a incomplete list of some rules of the algebra of infinitesimals. It's kind of a working rules. Well, here's the problem. these rules don't actually make any sense. So I'm going to point this out by considering, what should this be? What happens if you multiply two infinitesimals and then divide by an infinitesimal? What should you get? Well, if these rules were to be trusted, then on the one hand, notice this rule says that the numerator is an infinitesimal. And then this rule says, well, if you're dividing an infinitesimal by an infinitesimal, your answer should be finite. On the other hand, if you look at this rule as relates to that says that this should be finite. And then this says finite times infinitesimal should be infinitesimal. So wait a minute, what's going on here? This thing that we were just asking about, which is it? Is it finite or is it infinitesimal? This doesn't make sense. Right? So there are huge problems in trying to make up a consistent, reasonable way to talk about anything that could be reasonably discussed as infinitesimals. And the beautiful thing about it is we don't need them. We just don't need infinitesimals at all. They're only discussed as, again, sort of a way of avoiding having to talk about Riemann sums, which is completely pointless. Not only should we not want to avoid Riemann sums, we need Riemann sums. Right? We need to be able to talk about applications. We need to be able to connect those applications to something that allows us to use the fundamental theorem. Riemann sums are a good thing. They're not to be avoided. So, they're not real numbers. Now, I'll point out that yes, there are ways to make some sense out of infinitesimals. This isn't it. Right? This isn't it. All of that is contradictory nonsense. Right? Nevertheless, it can be done, but what remains is they are not real numbers. And therefore, it's highly suspicious to want to use them in some discussion of real problems that want real answers. Okay. Last thing I want to talk about, a little bit of terminology. What's the difference between integrals and antiderivatives? These terms are conflated very often, unfortunately. And we've already talked about the definition of an integral several pages back. Integrals are Riemann sums. So now let's talk about antiderivatives. What's an antiderivative? And here is a definition of antiderivatives. And I'm going to specifically refer to an antiderivative. Right? There are lots of antiderivatives for a given function. And I just want to talk about a single one. So an, not the. Okay. So importantly then, notice that the definition of an antiderivative, this is very different than the definition of an integral. Integrals are Riemann sums. Antiderivatives are not. Right? This is a very different definition. So they have very different definitions. They're also very different in type. If you're talking about, hey, I want to do an integral, well, we apply an integral to a function defined on an interval. You need to tell me both the function and the interval. That's not how antiderivatives work. Antiderivatives, if you want to take an antiderivative, you take an antiderivative of a function. Furthermore, we get different answers. An integral, ultimately, when you're done computing it, is a real number. That's what an integral is. And fundamentally different, an antiderivative, it's not a real number. An antiderivative of a function is another function. Okay, so these are not only not the same thing, they're not even the same kinds of things. All right. Okay. All right. Now, so why do students tend to conflate them? Well, it's because of the fundamental theorem of calculus. The fundamental theorem of calculus shows a strong connection between integrals and antiderivatives. Here's our fundamental theorem of calculus, the final formula anyway. And, well, on the left we have an integral. On the right we have a formula that involves evaluating certain values of this function called the antiderivative. This is a very strong connection between integrals and antiderivatives. That does not mean that they're the same thing. They are clearly different things. Okay, so why does this matter? So, related to this connection that comes up between integrals and antiderivatives, this function here, the antiderivative, is sometimes referred to as an indefinite integral. This is a bit of terminology. This is one of my least favorite bits of terminology in math. This terminology is an attempt to kind of, I'm going to say, celebrate what the fundamental theorem gives us, that, hey, look at this, there's such a strong connection between integrals and antiderivatives. It's like antiderivatives kind of are integrals or something. But let me explain now why I think this is really bad terminology. It remains that these are importantly different things, right? And if we use indefinite integral instead of antiderivative, that makes it sound like antiderivatives are integrals, which they aren't. So these are importantly different things, and the terminology here, indefinite integral, conceals that. Okay. Also, and I think this is an equally important point, this terminology, indefinite integral, kind of conceals the theorem itself. Right? One of the amazing things, arguably the shocking thing about the fundamental theorem of calculus, is that there is a connection between two very different things. That Riemann sums can be computed with a formula that involves something that doesn't look at all like Riemann sums. It's computed with something that's defined ultimately in terms of derivatives. Two very different ideas, two very different definitions that are connected. So that's what the amazing thing about the fundamental theorem of calculus. Now, if you change the terminology, if you use this term indefinite integral and don't say antiderivative, then what does the fundamental theorem of calculus seem to say at this point? Well, it seems to be that the fundamental theorem of calculus is saying that integrals are equal to integrals. And it's not clear why that's something that we should be impressed with. So I think this is a bad thing. It's important that we see what the theorem is and why it's interesting. Okay, so my advice to students is to simply don't use this terminology, indefinite integral. I don't think it serves a purpose. The definition of indefinite integral is, well, it's as an antiderivative. So just say antiderivative. That's what it is. It's not like it's more syllables. Right? So what's the point? What's the advantage of using the term indefinite integral? I don't see an advantage. Okay.